Okay. Good morning, gentlemen. Today is Wednesday, April the 8th, and today we are going to talk about section 11.2 uh, on balanced torques. All right. You'll recall from the other day that Monday, I guess, that we were talking about what a torque was. And a torque is actually simply a rotational force that causes an object to spin about some kind of axis of rotation. And the examples that we talked about had an axis at one end and then a length, a handle, or something like that on the end. And so the torque was the amount of force that you apply to the handle times the length of the handle. Now, what if that axis of rotation was actually in the center of the object, such that there was a torque on either side of the axis of rotation? All right. An example of this would be holding a long object, whoops, like this kid's toy that I've got, or not. So if I want to balance this thing on one finger, I've got to hold it right at the center of gravity. That's where the axis of rotation is going to be. If I try to put my finger over here, it's going to just fall. All right. And so that's not going to work. Now, what if the forces that you apply to either, damn it, the forces that you apply to either side of the kid's toy or the uh, a seesaw or a meter stick in the classroom. What if those applied torques were not located in the center, or I'm sorry, were not even on either side? What if you applied a greater force to one side than to the other? Would it still work? Could it still work? Well, the answer is yes. Okay. In the case of let's think about this. All right. Have you ever taken a trip to a playground where there was a seesaw or a teeter-totter sitting there? Or have you ever seen an adult playing with a kid on a seesaw? All right. Well, it is still possible to ride the seesaw and go up and down and up and down if there is one person who is applying a great deal of force, has a bigger weight, then and the other person has a very small force. And so the moral of the story here is that torques can be balanced even if the applied forces are not equal. Okay. What this means is that if there's a torque on one side that's balanced by the torque on the other side, it doesn't matter what the forces are because you can adjust the position of the two objects such that the torques become balanced. All right. So and the example here is two kids of unequal mass sitting on a seesaw. Okay. If this is the case and you've got a big kid and a little kid sitting on the seesaw here, you've got person A and person B. All right. We know that the torque of B has to equal the torque of A in order for them to be balanced. So that means, crying out loud, that the force of B times the displacement of B has to equal the force of A times the displacement of A. Now, look at the forces that are shown here. All right, the force of the weight of kid B is 500 newtons. The weight of kid A is 1,000 newtons. So this is 500 times distance B, which is our big fat question mark right here, must be equal to 1,000 times distance A, which is 1 meter. Well, 1,000 times 1 is, of course, 1,000. Wow, that's really bad handwriting. So what's going to be the value of distance B? Well, divide both sides by 500, and we end up with distance B has to equal 2 meters. Now, does that make sense? Sure, it does. Because if person A weighs 2 times as much as person B, then person B has to be 2 times as far away from the axis, the fulcrum, as person A. And so the torque is still a balanced torque, and this is why a big kid and a little kid can actually work on the same seesaw together without just the fatty McFat sitting on the ground and the little kid way up in the air somewhere. All right, so that's all I've got to tell you for today. So enjoy the Easter holiday, which is coming up. I will not see you again or talk to you again until the 20th of April. So enjoy your Easter and have a great spring break. Or not. There we go.